Hello guys, let's continue our discussion on compression members. So let's take a look on some of the aspects considered in column stability analysis. So the first consideration is on flexural buckling failure. So we have actually three types. We have the elastic, the inelastic, and the yielding. So most often than not, these first two here are more critical than the last. Okay, the yielding, the failure. So these are actually the limit state condition on strength. Okay, so these are more critical than yielding. So this is a more brittle failure than yielding, because yielding is always ductile. Okay. So for the second one, this local buckling, we will be treating this later, separately, discuss this. And the last one here, which is the lateral torsional and the torsional buckling, is more common to beam columns. Okay, so these are more common to beam column problems. So let's talk now of flexural buckling. By the way, flexural buckling can also be regarded as the global buckling failure, considered for compression members, to distinguish it from a localized buckling mode of failure, which is concentrated on the plate elements. So the Aisc requirement for this, take note that your resistance is which is equal to FCRAG must always be greater. Okay, so for the criteria now, your VRN must always be greater than summation of gamma I cube. Okay, so I'm referring here more on the Lrfd requirements, because we will be discussing a lot on Lrfd and only a few on ASD, since we have proven that Lrfd is the more efficient, economical, and predominant strength methodology that we can use. So for your reduction factor, the compression reduction factor is often used to be equivalent to 0.90, and we all know that resistance and capacity are just names used sometimes interchangeably. So when I say design capacity, I also refer to the design resistance. And I have here a column strength curve on the basis of the Aisc Lrfd criteria. Okay, so I have here an Lrfd criteria. Okay, so this green and red here simply considers your reduction factor phi c. Okay, so it slightly drops from a higher capacity to a slightly lower capacity. But I'd like to emphasize this limit into which your inelastic buckling failure mode and elastic buckling failure mode are separated. And take note of the graph of the column strength curve is actually your FCR uh, versus your slenderness ratio KL over R. Okay, so you call this now your slenderness of ratio factor. Okay, and you call this now your strength or your critical buckling load or stress. Okay, so this is the critical buckling stress. Okay, for the elastoplastic material, so these are the perfectly plastic range of your FCR, which is maximized at Fy. And this curve here happens to be your Euler curve. Okay, Euler buckling load or stress rather. Okay, and the limit of this is simply the CC that I am referring to. So this is your CC, which is equivalent to the same as your value square root of 2 pi squared E over F1. Okay, the only problem is your instead of using a 2 here, Lrfd, okay, since this is an Lrfd consideration, Lrfd uses lambda sub c equivalent to 1.5 instead of square root of 2. Okay, so instead of square root of 2, your Lrfd uses a value of 1.5 square root of pi squared E all over F1. Okay, so I have a derivation here on this on the other video. So you just take note of this. These values because I want to demonstrate more on this lecture the solutions to problems rather than the conceptual derivation of the equation. So for the Lrfd formula, trying to look at the graph here, so the inelastic buckling and the elastic buckling would be computed on the basis of these two formula, where your Fy over Fe is simply equivalent to lambda sub c squared. Okay, so this is now your basis for the lambda sub c. So other books you will see here an equation of 0.658 to the lambda sub c squared times Fy. Okay, other books here you will see a 0.877 Fy over lambda sub c square. So this one. Okay, so just place your Fe is equal to Fy over lambda sub c square. So it depends upon how the book will introduce to you the parameters involved. So I have here now a comparison between the Lrfd and the Aisc formula, and an additional residual stress method to show you a comparison on how the column strength curve compares. No? So if you will look into this graph, which is the more conservative? Do you think is the more conservative? Which is the more efficient? Etc. Okay, so by the way, this black here graph is the SRC curve parabola, which is the ASD. Okay, and this red here is actually the column strength curve using the residual stress, and you see down here the Lrfd equations. Okay, the pink and the green, okay, are the Lrfd, and this is the Euler. Okay, Euler curve. So the Euler curve is both used in as a continuation, no, of your SSRC parabola for the ASD, and the CSC curve for the residual stress method. Okay, so we will be focusing more on the Lrfd technique in solving some problems later in this lecture. Thank you very much.